Hi, everyone, and welcome to the final lecture of this course, of the PCP course in the entire MSRI summer school. It's going to be a fun one. We're going to talk about applications of PCP and of PCPs, and also a bit about applications of IOPs. We're going to talk a bit about cryptographic proofs, hardness of approximation, and also discuss some open problems at the frontiers of probabilistic proof at the moment. And hopefully by this point, you have all of the preliminary knowledge that you need in order to start conducting your own research in probabilistic proofs. So without further ado, let's dive right into it. And I want to talk about the possible applications of PCPs. So there are quite a lot of appealing applications to PCPs, and they range from quantum computing and cryptography and pseudo-randomness. It also interacts with areas of pure mathematics. For example, regarding Cayley graphs and embedding of metric spaces, it's quite a rich. There's quite a rich selection of applications of PCPs. However, I want to kind of focus on maybe the two most prominent and well-studied applications of PCPs. So here we'll only talk about two directions. So the first direction is for people who are, kind of glass half full type of people. And that's where we use PCPs to get a positive scheme for delegation of computation. And the idea is that what we do, so suppose that you have some computationally limited device. It could be your desktop computer, which I tried somehow to draw. And we want to solve some hard problem, maybe, color some, like doing some tree coloring of a graph or something along these lines. And, this is too hard of a problem for our computer. And maybe we want to delegate this computation to the cloud. Or maybe it's a large quantum computer that exists, and we want to perform the computation on the quantum machine. And think about any, doesn't have to be a cloud, any stronger computational party. And it could even be this party which is which has the same amount of computational power, but maybe it has some additional knowledge. Like, for example, it could be maybe they have access to a better type of information. So, the standard way of doing delegation of computation, which is what is often done right now, for example, when I'm using Gmail to do my, delegate my computation on the cloud, or any, Wolfram Alpha or something like that. What I do is I trust the server completely blindly, right? And I'm kind of like, taking everything that is important to me, and I'm sending it freely over the net, and I'm getting some answers, and I blindly trust them. But suppose that we want to be able to verify that the computation that we delegated is actually correct, because maybe the cloud tried to cut some cost and give just like some weak approximate answers, maybe just made an honest mistake. So if we want to verify it, we'll see how PCPs admit quite appealing ways of performing delegation of computation, and often in a zero-knowledge way, and with lots of nice properties. So that's the positive side of things. And in the negative side of things, specifically as a complexity theorist, this is something which is quite appealing to me. There is how we can use PCPs to prove lower bounds and prove the impossibility results and limitation of computation. So this is the glass half empty type of perspective. And that's hardness of approximation. So, we'll talk about it soon in more detail, but we have lots of problems that we want to solve, but they are just too hard. They are known since the 70s to be NP complete. And so, we can't hope to solve them. But maybe we can settle for an approximate solution. So, maybe we want to do tree coloring of a graph. And we know that this is something which is NP hard, so we don't expect to just like solve it. But suppose that I want to give some coloring that would satisfy most of the, so in free coloring, I want that every edge would have different colors at the end. So, this is here some free coloring that I made, and it's not perfect. Here we have like these two monochromatic edges, which are a violation, but maybe if we can get something which is nearly a perfect coloring, that would be good enough. And it turns out there is an extremely intimate connection between PCPs and approximation algorithms, and we'll see how we can prove hardness result using that. So these are the main two directions that we'll talk about today, and we'll start with this delegation of computation. Okay, so remember that in lecture B.8, we showed the following result. So this is the logarithmic time verification result. So we stated it for an x, but the whole thing gracefully scales with respect to any time complexity here. So think about when I'm writing here n time, this is non-deterministic time. So if I'm writing instead of t poly, then this would be np. And if I write instead of t exp, then this would be nx. Right, so the result that we saw in its full generality, it shows that if you take any language that using a proof can be solved in time t, then we have a PCP where the proof length is polynomial, the prover time is also polynomial, the query complexity is polylogging t, and the verifier time is is poly in n and log t. So, where n is the description of the object and t is the length of the computation. Okay, so this is an extremely appealing notion, and just like to kind of remind you how the picture looks like, then we have this prover here. The prover gets an explicit input x and maybe some widthness w. This could be like the tree coloring of a graph. It operates in polynomial time. It generates this PCP oracle. And then we have a verifier, which makes only polylog many queries run in time, which is poly n and log t. So this could be like logarithmically fast, like exponentially faster than the size of the computation. And then it gives us, it gets an input and it gives us an answer. So this is apparently, this result originated in a very old paper by Babai, Fortneau, Levin, and Sadie. And even back then, in those early 90s, they had this amazing foresight of seeing the potential of such a theoretical result. So what they wrote is that in this setup, a single reliable PC can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untested hardware. And that's quite amazing to see that this was, this was something that originated back, I think, in the late 80s or the 90s, and it took about more than 20 years until such systems were actually being used and deployed in practice. But the potential here is huge. Like the ability to do computation exponentially faster using the help of a prover. Of course, this leaves an important problem, which is, how do we use this setup, right? And indeed, it turns out that the way or the path one has to go from this theoretical result into getting something which is actually usable in practice, that there's quite a long way to go, and that explains why it took so many time. That way it took decades. So let me quickly skim through the chat to see questions. So regarding the PC, Alexandros is asking, did the PCP construction we saw achieve polynomial time prover? And the point is that it depends on which construction, but specifically, the construction that we discussed in lecture B8, that the one which has, sublinear time verification, we said that if a witness is given, so I'm not saying that like, so suppose we're thinking here about, three coloring. So I'm not saying that the prover solves the three coloring by itself. I'm saying suppose that the coloring is known. And maybe, and you can think about setting, maybe it's because the prover generated the system. Maybe because it has an additional information. Maybe it's a huge computation that was, performed only once, and now we want to prove it to many settings. So that's an important point. But given the fact that the witness is known, like encoding it, it's done in polynomial time, right? And then in some sense, like all it means in this case is encoding it via low degree polynomials. Okay, and I see that this also answers the second question. Thank you. Okay, so what I want to tell you is how we can make this thing practical and show you a few steps towards achieving that goal. And for that, we'll have to do a crypto interlude. And the idea would be to transform the perspective from PCPs into interactive arguments. So at the risk of upsetting all of the cryptographers in the audience, I have to say, this is my perspective regarding cryptography, is that we try to do everything in the information theoretic setting. And we often reach at some point some limits. So this is where it's nice to add crypto, because you make some cryptographic assumption, and suddenly you have this like magical tools that you can use, which achieve much more than could have been possible otherwise. And let's see what happens here. So the theorem that we're going to kind of discuss here will be the following. Suppose that we have some language L or some problem L that has a PCP with a certain prover time, PT, verifier time, VT, and query complexity Q. So let's keep it completely, just a parameter for now. Then by using cryptography, we can construct an IP, an interactive proof for the problem, such that the prover time would be, well, roughly the same, and the verifier time would be roughly the same, and the communication would be roughly what the query complexity was, right? So if you have something, with polynomial approval time and logarithmic verifier time and maybe polylog query complexity, then this would mean that, we'll have this extremely efficient protocol. Now, can anyone tell me why I kept, doing L quotes whenever I said proof, and like, why isn't that a proper interactive proof?
I think we're not going to have soundness, so only computational soundness.
Yes, exactly. As Matthias said, like the moment that we use cryptography, it means that we will replace, the word proof with an argument. And what is an argument? An argument is a proof that only holds assuming the prover is, somewhat computationally bounded. So it's a proof system where, you have this prover, and as long as the prover is not crazy powerful, having exponential time resources, it won't be able to cheat. So that's the idea. And I think that the name argument is kind of nice because, it's not as decisive as proof, which is an absolute truth, but it gives you some argument, which as long as all parties are not overpowered, that would be enough. Okay, so let's see exactly how this thing works and how the query complexity. I think this is the only thing, like the interesting thing, which happens. How do we trade off query complexity for communication? So let's see. So, but before that, let's just apply the PCP that we got last time and see what we get. In this case, we get this scheme where you have a polynomial time prover, which gets an input and a witness. And we have some, polylog machine that can verify whatever language that it was, right? So the potential here is quite vast. And you might ask why, we kind of like saw that if we only have, communication, which is limited and very short, we had this like result regarding laconic provers. But the point is because the limitation result apply to interactive proofs and not to interactive arguments. So in fact, we can do better than one can even hope to do information theoretically. So let's start with a completely naive idea. So anyone has a suggestion, assuming you don't know Kilian's protocol, of how we can take a PCP and make it an interactive protocol? Anyone want to suggest an attempt? And please be as naive as possible.
Commit to the whole thing and then just decommit whatever the verified queries.
Yeah, fantastic. Exactly. So the idea is, think about the following scheme. We have a prover and a verifier. And, the verifier samples some randomness, which dictates the query structure and so forth. And it sends this randomness to the prover. The prover will produce a PCP string. And then instead of, instead of sending the entire PCP string, and then the verifier would query it, the verifier already specified the randomness, so the prover can see what queries the verifier is interested in, and it can just send these queries to the verifier, and then the verifier can decide based on that. Now, of course, this would have perfect completeness. I mean, if everything is behaving according to protocol, that this is fantastic. However, there is a big flaw here. Can anyone tell me what's the problem?
Soundness is kind of gone.
Sorry, I couldn't hear.
The soundness seems like it will just break.
Yeah, exactly. So soundness breaks because, the prover doesn't even have to produce this PCP string. It can just like say, well, I have a verifier and he wants to know this thing. So let's give it whatever whatever it will make the verifier accept without even looking at the problem or anything. Just, it's like just like let somebody hear what one wants to hear. So we want to have this way of making the prover commit to the PCP in a way in which he can't suddenly change his mind, in which we know that the query set, that the answer to the queries that the prover is sending indeed is consistent with the PCP string. And another argument is that I kept talking about the crypto and the crypto and the crypto, and here there's no crypto, right? So we have to do something. Okay, so this is, it's a beautiful protocol, and a classical protocol, which is called Kilian's protocol. And indeed, the idea would be to commit to the PCP string in a way which can be locally decommitted. So what do I mean by that? So for that, we need to introduce a little bit of crypto, just a minimal amount. This is the only crypto we'll have here, just these 2 lines. And we'll talk about family of hash functions, which are collision resistant. So maybe a nice picture to have in mind for this thing is, you look at some function, family of functions H, and they go from a large domain of size 2 gamma into a small domain of half the size. And it's half the size, so it means that each, the elements must, there must be a lot of collisions here. But the point in this hashing system is that it's a very, carefully chosen family of functions, such that any efficient adversary that wants to say, here is a point in the hashing, and he wants to give 2 different messages that would be mapped to the same point that would collide, then this is something which happens with a very small probability. And where I say here the probability negligible, this is actually something which is mathematically well defined. It means, the probability which is of L, which is so small that is 1 over any, smaller than 1 over any polynomial. So it means that any polynomial time, like adversary, will not be able to do it. Will not be able to find such a collision except with some, will not be able to find a collision. And this means, and this is exactly what we'll need. This is why things become here an argument as opposed to a proof, because if you run in exponential time, then you can just like, query everything and map everything, and then the things will break. Okay, so we have this notion of hashing, right? When we say that like the probability that like an efficient algorithm would be able to find these two different pre-images that would collide at the same point. And using that, this admits a natural protocol. And the protocol is as follows. We start by verifying, choosing at random one function in this family. And notice, this like condition regarding no collisions, it's always probability over a choice of a random hash function, right? So this is why the verifier has to choose the hash function as opposed to letting the prover, start with the hash function of each choice. And then what happens is we'll do the very common used idea, which is called a Merkle tree, which is a way of performing hash of hash of hash of hash in the setting of structure of a binary tree. So let me say exactly what this means. So we start, the prover will write down a PCP string, but it will not send it because we can't afford to communicate the entire thing. And then we'll have a tiny commitment to this string. So how do we make a tiny commitment? Well, we look at, let's say, this is the entire PCP string. So let's say that this is, pi 1 ... until pi L, where L is the length of the PCP. And so we look at two adjacent like blocks, or two adjacent symbols, depends on how we define this gamma. And what we do is we hash these two things. So, I look at the first two values here, this one, and then I hash them into this point. And then I go this point and this point, and I hash them, this point and this point, and I hash them. I do it for this entire level. And then I look at all of the hashes, and I do it again. I take in any two adjacent hashes and compute the hash of the hash. And, each time that I'm doing it, the size of the proof contracts by a factor of 2. So if I do it logarithmically many times, I'll end with just a single value. Just a single value, which is the hash of hash of hash of hash of hash of hash of everything. And, the intuition here is that if it's hard to find a collision, to find two cells that would get mapped to the same point, then it would also be hard to, somehow change this string and still be able to reach the same hash of hash. But we'll see that in a second. Okay, so, and then what we'll do, the prover sent this small amount of information, which is this Merkle tree, this hash of hash of hash of hash. And that would be our way to bound the behavior of the prover, so it won't be able to kind of like say, well, here is some information which has nothing to do with the PCP, just to make you happy. At this point, after the prover is already committed, we can actually send the PCP randomness. And the prover, it would do exactly what it did before, like look at the relevant queries that we want to make and send them to the verifier. But in addition, it would also produce an authentication path for each answer. So let me kind of explain what that means. Suppose that I care about querying this blue point, right? So the prover will take this blue point and maybe just like to clean it up a little bit. Yeah, so I care about this point here and think that there are L many symbols. So I want to be able to authenticate that this is a valid, something which is consistent with the value here. So the prover will also provide the value of this point. And then I can check that point. And it would also provide the value of this point. And then I can check that point. And also provide the value of this point. And this point, And then I can have a path that in which I can check everything. Okay, so that's the idea. And so I get these answers and also the authentication. And then what we do is, we first check that every query is authenticated up to the hash of hash that we wanted, because we can just, traverse the tree and go like this. And yeah, and then we can safely run the PCP verifier with respect to that, and in some sense we are happy. Now, what would be the time complexity in such a situation? Well, it would be the time complexity of the PCP plus, something which is linear, because we have to compute all of this, something which is linear in L, the length of the proof, because we have to compute this tree. The time of the verifier would be kind of the same. It would be as it was for the PCP, but also here we'll have these Q queries that we want to make, and for each of them we'll have to do this logarithmic path of authentication. And the total number of the amount of communication would be O of Q, because we send for each query we send some authentication path. So that's the whole idea. Now, the soundness analysis here is trickier than it seems, and we won't go into that here. But the same intuition which says that if a single collision is hard, then you can argue that that would get up to here. Okay, so and let's continue. So there's a question regarding whether this particular hashing setting gets broken by a quantum computer. That's a good question. And off the top of my head, my answer would be it really depends on the particular type of hash family. Because if you can derive a certain hash family which relies on something that quantum computers do really well, like hidden subgroup problems or things along this line, then that would be a problem. And if it deals with some things which quantum computers probably struggle with, then then we should be good. Okay.
I have a question.
Yes.
Just like before. So is my intuition correct that one cannot trivially apply Fiat-Shamir to make this non-interactive? So because it looks like that the prover has a huge degree, so that the randomness which is sent by the verifier determines the query set, right?
Yeah. So okay, this is a good point. But I guess that okay. So let me quickly talk about that. Or maybe I want to make sure that we have quite a lot of things to do today. So let's do the quantum discussion at the end, because it's not necessarily relevant for everyone, but let's do it right after the lecture and talk about that. But thank you. And for now, I want to focus on, something which is much more contemporary than the Kilian's protocol, which is, we saw how to take a PCP and transform it into an interactive argument. But can we do the same with respect to IOPs, which could be, potentially far, far stronger than PCPs? So suppose that I have this language that has some public coin interactive oracle proof, and it has, a certain prover time and verifier time and query complexity. And the gist of it would be that we can compile the same IOP into interactive argument roughly with the same parameters as we had before. So, the prover time would roughly be the same, the verifier would roughly be the same, and the main challenge would be to kind of trade off query complexity Q to communication of Q. And we see this is somewhat analogous, this is quite analogous to what we had before. So we can start with the naive proof attempt just to articulate what breaks in the interactive setting. So, we have a prover and a verifier. The verifier sends the randomness, one for each of the k different rounds. And then the prover thinks about all of it kind of computes in its head all of the oracles that it would send with respect to these messages from the verifier. And, it would deduce what would be the verifier's queries based on these randomness and just send the queries. So we have all of these oracles just restricted to the place that we want to query. And, the verifier would try to query this place. And exactly as we had before, completeness would remain exactly the same, will remain perfect, but soundness is bad because the prover doesn't have to, it's not committed to these oracles, and so it can just answer whatever the verifier wants to hear. And indeed, the way to take these IOPs and compile them and make them, transform them into interactive arguments is to extend Kilian's protocol from PCP to IOP, and using the same idea of Merkle trees, but in a careful way so that it would, the commitment would also port. So, okay. So, so let's see. As in Kilian's protocol, we'll again use collision resistance functions to build our Merkle trees. And think about your prover and your verifier. And the verifier would, sample one of these collision resistant hashes, send it to the prover. Now, the prover here would start with the first oracle and encode it using the Merkle tree, exactly as before. Then it would send this first commitment. At this point, the verifier would, send a piece of randomness. That would be the first round of the protocol. And the prover would, see this randomness, compute an oracle, commit to it using the Merkle tree, and send it again. And we'll do this whole game k times for each one of the rounds. And at the end, we can reveal the last amount of randomness, which will determine the verifier's queries. And so what the prover can do is, look at the set of queries and produce this authentication path for each answer that it provides, and send, the answer to the queries plus the path, in which way we kind of like check these authentications, and we can then just invoke the verifier with respect to the queries that we've gotten. Okay, and as you can see, the time complexity behaves exactly as you'd expect in this setting, right? Like we will picking this factor here for the Merkle tree, and also here and here, but the essence of it is that we're only picking a factor of q times log the proof, right? So this is quite desirable. And in some sense, it means that if we design efficient IOPs, then this leads to efficient interactive arguments. And in fact, one can further take this type of ideas and compile this thing into non-interactive arguments, into succinct non-interactive arguments, which are referred to as snarks. And in some sense, when we look today at actual proofs, how the actual proofs that are being deployed on blockchains and so forth, they're mostly consisting of authentication paths for the Merkle tree. It's quite funny that like this is the main bulk of what is happening there. Okay, so that's what I want to say regarding this delegation perspective. Any questions? So let's dive right into the complexity theoretic side, into hardness results, and talk about hardness of approximation. So, during the 70s and 80s, this is where, you look at the archive and you'd see dozens of new NP hardness reductions every day, and, circuit complexity results. This was happy time for the pessimists. And we saw that many of the key optimization problems that we care about are actually NP hard, right? Which is a big bummer or source of joy, depends on what are your goals in life. And this is, you know, we saw that like lots of important problems like 3-sat and knapsack and Hamiltonian path, traveling salesman, recoloring, click, and even playing Super Mario. It's all, you know, very hard. So it's only natural to say, what can we do? Let's try to settle for, you know, if something is impossible, let's try to use some approximate solutions. So, you know, I went over this at the beginning of the lecture, so let me illustrate this a bit more formally. So we say that an algorithm A is an alpha approximation algorithm for a maximization problem, pi, if for every x, we give a solution which is, you know, at most off by a factor of alpha. So just to kind of like give a better sense of, suppose we're looking at this tree coloring instance, this is a maximization. We want to get the maximal amount of edges which are not being which are not monochromatic. And so, you know, pi of x is the maximal number of edges which are not monochromatic, and maybe we'll get alpha half. So, you know, we will get something which messes up a bit of them, but it is a good approximation. So that's the name of the game. And of course, one can formulate exactly the same thing regarding minimization problem. Like if we just by, you know, replacing the order of the alpha, we can bring it here. Yes, and regarding Super Mario, then apparently you can implement a Turing machine by kind of like designing this path of Super Mario jumping on, you know, mushrooms and stuff. It's an amusing paper to read. Okay, so, you know, we have this notion now of approximation algorithms, and I want to give this concrete example of how we can use a PCP in order to prove the hardness of approximating an important problem, which is max 3-sat. So first of all, what is the maximization version of 3-sat? We're given this, you know, 3CNF formula. You know, we have like a bunch of clauses. Each clause is, you know, some variable or some variable or some variable. And the goal is to find an assignment which is not necessarily, you know, perfectly satisfiable assignment, but it is an assignment which satisfies, you know, is the largest possible amount, the largest amount of clauses that you can satisfy. Right, so, you know, you kind of take this bunch of clauses and you say, well, if I would plug here this value and that value and that value, then, you know, maybe I can get 4 out of these 5 clauses. So I want to make a claim, and the claim would tell us the following thing, that I want to show you an algorithm which gets a 7/8 approximation polynomial time algorithm for max 3-sat. So it means that we can always get something which is, you know, up to a factor of 7/8 as good as the optimal assignment for any possible formula. Does anyone has an idea how one can try to design such an approximation algorithm? So I'm going to be, this is like the, so yeah, Shafik mentioned something which is exactly the right answer. Thank you. It is the probabilistic method. But in some sense, I will do it by presenting the most annoying algorithm possible. And what would be the most annoying algorithm possible? Like, the algorithm would say the following thing. Well, how do I get a 7/8 approximation? Well, I'll prove to you that like any 3-sat formula whatsoever can always be 7/8. Like you can always find an assignment which is, you know, 7/8 of fraction of the clauses are being satisfied. And more than that, I don't even have to be greedy about it. I can just pick one at random because there are so many of them, right? So the main idea, we made this observation. We saw that, you know, we see that like first, every assignment has something, every formula has an assignment that would satisfy 7/8 percent of the assignment. And we see that there are actually lots of them, so it suffices to choose a small number at random. So let me try to convince you that there exists this approximation time. So, let's denote by CI an indicator of whether the ICE clause is being satisfied by a random assignment, right? So I'm just like saying, I plug in some random values to the clause CI and see what happens. So if we look at the expected value, this is the expected value of an indicator. So it's just like, what is the probability that the clause CI would be satisfied by a random assignment? And this is for every clause, doesn't matter which clause. And the answer is 7/8 because there is only one way for a disjunction of 3 variables to take a 0 value, right? Because it's all 3 variables, so you have 8 different assignments and only one of them is not satisfiable. And now we can do linearity of expectation. So if we want to count the number of satisfied assumptions, and this is exactly the sum of all of these CIs, and we take the expectation. So by linearity of expectation, this is exactly like the sum of the expectation, and this we computed, so we're getting just 7/8m. So this means that we always have this assignment that would satisfy 7/8m variable. By the way, m here is the total number of clauses, I should have said that. So a fraction of 7/8. And moreover, if we do, the regular tricks of concentration of measure, like just, simple Markov inequality. I mean, so first is to make it in 2 steps. Like the first is, if the average is 7/8, then it must be the case that some assignment get at least 7/8, which is funny. There is a rather famous Israeli politician who kind of made a statement on TV that like all of the citizens are making less than the average salary at some point, which was a funny thing to see. But politicians, Anyways, and if we apply Markov inequality, a way of like looking at it, you can say, the probability, like how many percent of the population can make 5 times more than the average salary, then it could be at most 1/5. Otherwise, the average salary would be too high. And so you can easily show that there is actually a large fraction, something like 1/the number of like different clauses that would satisfy. And so you sample at random these O(m) random assignments, this poly time, and you're happy. Notice that like checking whether a given assignment is satisfiable, this is definitely polynomial time, in fact linear, and so we're all happy. So this shows us, just an example of an approximation, an annoying approximation algorithm. And annoying because we didn't do anything, we just argued that there is always a trivial solution. Okay, please stop me if there are any questions. So now I want to show you this nice connection between hardness of approximation, between like approximation algorithms and PCP. But like if you think about it at first, it might seem completely unrelated, right? I mean, on the one hand, it's a way of proof systems, which you use them by only making a small number of queries to verify statement. And this is an approximation algorithm. It seems like completely non-related thing. But in fact, there is a very, very tight and intimate relation. So first of all, if we want to show hardness of approximation, we need to say what we mean by hardness of approximation. So we used to show lower bound or possibility result by saying something is NP hard. But NP hard is a notion which we defined for decision problems, for yes or no, 0-1 type of problems. Whereas this is an optimization problem. It's not about, whether there exists a coloring or not, whether there exists a satisfying or not. It's about, compute the maximal satisfying assignment or something along this line. So the way to capture the hardness of approximation problems using decision problems is by looking at gap problems. So what would be a gap problem? It's a problem where you have, 2 different settings, and you want to know whether you're greater than one of them or smaller than the other one, right? So for example, let's be concrete. Let's think about this max 3 sat. So we want to know whether there exists an assignment which satisfies, let's say 7/8 plus epsilon, like a little bit more than the trivial thing, or everything must be, at most 7/8 hard, right? Or just like setting 2 thresholds. And I want to show you using, a 2-line proof that, if this problem is hard, then also approximating is hard. So if what we want to show is impossibility result, it suffices to focus on this decision problem. So what exactly are we going to do here? We want to show that if we have this gap problem, and the gap problem is NP hard, then it is NP hard to approximate to precision, which is S/C. So what does it mean NP hard to approximate? It means that if I had an efficient algorithm for approximating pi, then I can solve this NP hard problem of the gap. So how do we do it? So it's a simple idea. So we start with this gap problem and we reduce it into an approximation problem. So if the solution, there exists like a solution which is past the threshold of C, then the approximation have to give us something which is at most worse than C in a factor of S/C, just because this is how we define the precision, like the 1/alpha. And S times C/C, this is just S. Whereas on the other hand, if it's less than S, then, well, it's less than S. And so this means that if you can solve an approximation problem, then you can just use this algorithm in order to solve the gap problem. So it suffices to just argue that the gap problem is hard. And now finally, we can see the connection between PCPs and hardness of approximation. And, rather than, this is like an extremely rich area of research where each small parameter is incredibly important. But I want to kind of like show you with the running example that we had, just to make the connection clear. So I want to show you the following theorem. So suppose it's NP hard to approximate the problem of gap 3 sat. Right? That we take 3 sat and we want to determine whether there's an assignment that satisfies everything or at most a fraction of S. So we want to show that this problem is NP hard if and only if 3 sat has a PCP with logarithmically many randomness, which will mean polynomial size in turn, and 3 queries for some soundness parameter, so the completeness, perfect completeness, and soundness parameter S prime. So just to kind of like clarify, first, we saw that approximating like that we can always get a 7/8 approximation. So it means that this problem gap 3 sat of 1 versus 7/8, this is trivial. So this would be for some constant, which is some epsilon that would make this bounded away. So it would be 1 and 7/8 plus epsilon plus a small chunk, small constant. Okay, and this theorem, this is the PCP theorem, which we sketched. We solved the component and we sketched it last time. So now we're going to do a proof, and for the proof we have to do these 2 directions. So the first direction to see, we'll kind of say, suppose that gap 3 sat is NP hard. Now let's construct a PCP for it. So can anyone has an idea? How do I suppose that I know that the gap problem is NP hard? How do I use this problem in order? How do I use it to design a PCP? So let me walk you through a nice idea. So this would be exactly the jam principle that we said. So what we'll do is we'll want to show a reduction from 3-sat to gap 3-sat, right? Because we want to show that this is NP hard. And how do we show that this is NP hard? We take an NP complete problem like 3-sat, and we saw that it reduces to the problem that we care about. So we're starting with some 3-sat formula. And then what we do is we reduce the 3-sat formula into the gap 3-sat because we have this hardness result, right? So we apply this reduction. And so we've taken this 3-sat formula, and the 3-sat formula had just, this small number of corruptions. It could have, okay, so this 3-sat formula, like this is the problem. So let me kind of like say it. I think I might have confused you, so let me do it more in a range way. So I'm starting with this hardness result, that the gap problem is hard and I want to construct a PCP. So how do I do it? I'm saying, if this is hard, then it means that I can take 3-sat and reduce it to gap 3-sat. So this means that I'm starting with an instance of 3-sat, which might only have a single clause, which is not satisfiable. And then what I'm doing, I'm transforming it into a gap 3-sat instance, where, either it's perfectly satisfiable or there's a significant portion of clauses which are not being satisfied by the definition of the gap problem. And then we can just give an NP proof, which corresponds to the gap 3-sat instance, and we can just sample clauses at random and until we hit it, right? Because like what happened is that we started with a problem. Well, we might have only a single clause, which is bad. And this means that we have to probe at random every clause in order to catch it. And we gotten something which kind of like tell us, well, at least 10% of the clauses would be bad. And so let's take 100 clauses at random, and that would be enough. So that's this side of thing. And there is also the other way around, which is what we need to show hardness of approximation result, which is the following. We'll say, suppose that we have a PCP. How do we prove that gap 3-sat is hard? So how does this existence of PCP implies that gap 3-sat is hard? So the idea is, we'll take 3-sat and we'll reduce it into gap 3-sat. But how will we do this? We need to kind of like get this reduction. So this is where we actually use the PCP verifier. So we look at the insides of the PCP verifier, and it's an algorithm. So we can apply the Cook-Levin theorem in order to represent it as a 3CNF formula. But this is an algorithm which, in the completeness case, it satisfies with probability 1. So this would be a formula which is fully satisfiable. And the soundness would say that the thought that the amount of things we can satisfy would be at most a S prime. So now if you take that, just going back, it means that the gap problem is hard, and because the gap problem is hard, then so is the approximation problem. So before I want to, I want to have time for a bit of discussion and answer questions. But before that, I just want to say a few concluding words regarding the summer school and where we're at. So I think that the field of PCPs is now, and interactive proof is now experiencing a renaissance, which is why both Ale and I are so excited about this particular point in time. So to give a bit of context, so ever since the 80s, these notions of proof systems and interactive proof systems and PCPs, we've gotten into this was a focus of attention, and this led to the Turing Award of Micali and Goldwasser. So this is like a central point in the theory of computation. But at least with PCPs, what happened is that quickly this connection between hardness of approximation and PCPs was formed. And even though the notion was, it was introduced because of the potential of, positively using PCPs to verify computation efficiently. What happened is that PCPs became as an intermediate tool to proving lower bounds and hardness approximation results. And for a long, long time, this field, of hardness approximation was extremely at the source of attention. And slowly, we've reached some barriers. And though I have to say that some of the most interesting open problems in all of the theory of computation involve this field. For example, I have to pose one problem, which this for me is one of the most interesting ones, is whether we can construct a PCP of, constant queries, like 3 queries, like the PCP theorem, but of linear length, where the blow up is like really just linear. And this, the beautiful results which got quite near to that, but we're still not there. And this has been something that people try to do, and the effect of this would be amazing. We get amazing results in complexity. We get amazing positive results for delegation. This would be something, truly groundbreaking. And in some sense, it led to beautiful mathematics being introduced to theoretical computer science. For example, the whole notion of high dimensional expanders and algebraic geometry codes and cohomology and perspectives and algebraic topology. So it brought a lot of beautiful mathematics into this field. And in some sense, I think that the exciting field of high dimensional expanders is one of the most promising directions that I know of getting this goal. But going back to my main line of thought is that, we've reached a certain, saturation point, and results became harder and harder to come by. And only recently, in the last, 5-6 years, there is this new wave, a new, strong, renewed interest in PCPs and IOPs, where we're looking for the original motivation of using PCPs in order to, to do good, in order to achieve algorithmic tasks, in order to delegate computation. And it's quite amazing what's happening. It seems that every day new amazing things are happening, and there are deep connections to quantum computing, and there are deep connections to many other areas of mathematics and computer science in general. So I hope you enjoyed this summer school. I hope it gave you a bit of taste and at least all of the preliminary knowledge that you need in order to start doing research. If you have any questions, please feel free to contact all of us. We'd love to talk about it. We'd love to suggest concrete projects. I think there are so many fascinating problems to attack here. And I would be extremely interested in talking to people and get people excited and working on these problems, which I very much want to see resolved. So thank you, everyone. I'll stop the recording and take some questions and discuss.